The last few times we've been looking at the thermodynamics of chemical reactions, we derived this basic and important relationship between the Gibbs free energy change, or driving force for a chemical reaction, and this reaction quotient, which involves all the concentrations or activities of all the reactants and products. We also looked at the relationships for the standard state Gibbs free energy, that is the driving force that exists when all the reactants and products are at their standard states, and we'll talk a little bit more about what those standard states are later today. And we talked about what the reaction quotient is, and we talked also about what happens when the reaction is at equilibrium. We talked about the fact that the reaction quotient is equal to a constant, which we call the equilibrium constant when we're at equilibrium, and that the equilibrium constant, yes, can then be used together with the definition of the reaction quotient in order to calculate or predict what the equilibrium concentrations or pressures or other measures of activity will be when the reaction is at equilibrium. I emphasized at the time, and I'll re-emphasize now, that the equilibrium constant can be interpreted as the number of microstates available to the universe when the products are at their standard state, divided by the number of microstates that are available when the reactants are at their standard state. In other words, the equilibrium constant is a measure of the change in the number of microstates available to the universe when the reaction takes place. And that's because the microstates are related to entropy, which is related to driving force. That makes the equilibrium constant an extremely important property or quantity for understanding how chemical reactions behave. Right, that's all from previous times. Last time we did we did one example. We're going to do several more examples this time for how all this works. The example in this case is, last time it was a chemical reaction. This time it's not really a chemical reaction. It's a partitioning problem, one that's relevant for an awful lot, a whole ton of biology. Let's suppose we have a lipid membrane. Of course, all cells are surrounded by lipid membranes, so lipid membranes are ubiquitous in living systems. And surrounding the lipid membrane, of course, is some kind of aqueous solution. And let's suppose that in that aqueous solution there's some kind of molecule which is hydrophobic. In this example, doesn't have to be hydrophobic, but let's suppose it's hydrophobic, which means that using the like dissolves like rule, we should expect that this hydrophobic molecule will be soluble or more soluble in the greasy interior of the lipid membrane than it is out in the polar hydrophilic water phase. We know that that's likely to be true, but we'd like to explore that idea using the standard thermodynamics that we've been developing over the last couple of times. So let's consider the ligand L, first in the water phase, transferring itself to the membrane phase. So L1 goes to L2, L1 is in the water, L2 is in the membrane. And let's assign a delta G at standard conditions to that transfer. Now, this assignment doesn't come from any thermodynamic tables. It's just a number I pulled out of the air for use for illustration in this particular case. So 10 kilojoules per mole is, let's talk a little bit about how big that number is. Remember that at room temperature, the quantity RT is about 2.5 kilojoules per mole. So what I'm saying in picking this value is that it's about 4 times bigger than RT. That means it should have a significant effect, right? If I pick a delta G value that's less than RT, then it's not going to have very big effects. If I pick a value that's way bigger than RT, and this is kind of in the middle of that, then it will have a big effect. So I'm picking a number that's big enough so that we expect, and also notice that it's got a minus sign, which means it's favorable for the L to go from the water into the greasy interior. So I'm picking values that should mean that I'm going to expect to see At equilibrium, I'm expecting to see a higher concentration of L in the interior of the membrane than out in the water. We're doing all this at 300 K. That's the standard temperature, near room temperature. I'm also going to say that the exterior water solution here is a chemical potential bath. I'm saying that the total concentration of L out in the exterior is 1 millimolar. And I'm asking, okay, given this, and given that that can't change, given that the outer water solution is so large that no amount of dissolving into the membrane is going to change this exterior concentration, I'm going to ask, given that condition, what is the concentration that I expect in the interior? Yes, so the water phase is a chemical potential bath, and that means that the concentration in the water, which is the same thing as the concentration for total, is a fixed quantity. At equilibrium, I know that the reaction quotient is equal to the equilibrium constant. And in this particular case, for this particular simple reaction, the reaction quotient is equal to the ratio of the concentration of L in the membrane to the concentration of L in the water phase, which is the same thing as the fixed total concentration. And that means that the concentration in the membrane is just K times the concentration in the water phase. And so everything boils down to just calculating what this K is. We can use K is equal to e to the minus delta G 0 over RT. We have our delta G0 value above, so it's just a matter of plugging in. The minus sign together with this minus sign here means that we're going to get an e to a positive power, which means we're going to get a K value that's bigger than 1, right? E to something positive is greater than 1. E to something negative is less than 1. So if delta G is a positive value, you're going to get a small k value, something less than 1. But if delta G is a negative value, which is the case here, negative 10 kilojoules per mole, then we're going to get a k value greater than 1. Looking at this, that means that we're going to get a greater concentration in the membrane than there is out in the water solution. That agrees with everything that I said earlier and our intuitions about how all this system should behave. With the values that we have, we get K is equal to about 55. K, the equilibrium constant values vary over an enormous range. A value of 55 is a rather small favorable equilibrium constant. An equilibrium constant greater than 1 means that at standard state conditions, the reaction, in this case the transfer of L from water to membrane, will be a favorable reaction. Will favor the products rather than the reactants, and this 55 tells us by what ratio the products will be favored, in this case over 50, a factor over 50. That means that the L concentration, just plugging into here, the L concentration will be 55 millimolar in this case, right? The total concentration out in solution we took to be 1 millimolar. K of 55 means there's going to be a 55 millimolar concentration in the membrane, which means that the membrane effectively concentrates our ligand, our L value, by a factor of about 55. All right, all of that is the standard kind of thing that you expect in this case. And I went through it fairly carefully so that you can have similar kinds of feelings or expectations facing any other kind of problem of this sort. All right, the next example is a somewhat more complicated one, right? The reaction up above was just a transfer from one phase to another. Now we're going to look at the hydrolysis of ATP. That's a much more complicated reaction. Still not a terribly complicated one, but a much more complicated one than the last time. And also a very important one biologically, of course. The hydrolysis of ATP is the sort of power, the chemical power source for most of the machines in a living thing. It's utterly necessary for all living things to have machines that are powered by ATP. ATP is the fuel for all those machines. So this reaction provides the energy that drives most of the chemical machines in the cell. The delta G0, so let's look at the reaction. It's ATP, which has the T stands for tri and the P stands for phosphate, so adenosine triphosphate with a water molecule cleaves off one of the three phosphates to form diphosphate, ADP. And in the course of that cleavage, the delta G value is about minus 31 kilojoules per mole at standard conditions. Now, the conditions actually inside the cell aren't standard conditions. And so what we're going to do in this problem is calculate what the driving force is due to the fact that conditions inside the cell are not standard. The conditions I'm going to give, in fact, are fairly typical of conditions inside many cells. And so we're going to see what the delta G, what the driving force is under typical cellular conditions rather than at standard conditions. Standard conditions really have nothing to do with biology. They're chosen by chemists for convenience. They're not chosen for what's biologically relevant. So the delta G we're going to calculate is actually the more relevant quantity. This delta G at standard conditions is often quoted, and it's often, kind of fine for a rule of thumb sort of intuition for what's going to happen. But the real delta G driving value inside a cell is quite different. Let's see how different. All right, so yes, what is the delta G when the ATP concentration inside the cell is 3 millimolar? That's a typical concentration for ATP. The ADP concentration inside the cell is only 1 millimolar. Notice that we've got a little bit of an excess of ATP in this case. The ADP concentration is a little lower. And then finally, the pyrophosphate concentration is about 20 millimolar. This is a product of reaction. This is a product of reaction. This is a reactant. And of course, the water concentration, that's the solvent. It's present in high concentration. That's the fourth chemical species in our reaction, and we'll see what to do with that. We don't give the concentration of the water because it's not changing and because it's high. And all of this is happening at 300 K, near room temperature. Cellular temperatures are usually, well, inside of a human body anyway, are more like 310 K. And if we change the temperature, we'll get a somewhat different answer than we're getting here, but 300 K is the temperature for cells outside of a human body, so for a bacterial cell in a pond or something like that. So it's also a relevant temperature. All right, so our formula is delta G, the driving force. The true driving force is equal to the standard state driving force plus this extra term that accounts for the fact that we're not at standard state concentrations. And we need to calculate, in order to use that term, we need to calculate the reaction quotient. The reaction quotient is given in terms of activities in general. And one of the things about this particular case is that at least one of these activities is for the solvent. And so we're going to choose a somewhat different expression for activity for the solvent than we do for the other three. So we choose. We're free to choose these activities, the expressions for these activities to a certain extent, but we have to choose definitions that are compatible with the standard states for the delta G values that we use up above, right? This delta G value that I chose up above assumes a certain standard state, and we have to choose definitions of the activity that are consistent with that standard state. So the standard state that applies for this particular choice of delta G is that you're at 1 molar concentrations for all species, that all pressures are at 1 atmosphere, and that the solvent is pure. Under cellular conditions, none of those conditions apply, which means our activities are not at standard state, but we have to choose standard state conditions in our definitions of the activities that match with these standard state choices. So we choose the activity for the ADP to be the molar concentration of ADP divided by the standard state molar concentration. Our standard state for this delta G is this one here. So we have to choose this 1 molar denominator in our definition of the activity. We're constrained to do that. Likewise, likewise for the pyrophosphate, molar concentration divided by the standard state molar concentration. For ATP, molar concentration divided by the standard state molar concentration. But for water, which is a solvent, the standard state condition is for pure solvent, and the choice for activity that goes with that is the mole fraction for the solvent, assuming that all the dissolved species don't represent much of a mole fraction, that water is the dominant chemical species inside the cell, which is in fact the case. We make an approximation here. This is not actually accurate, but it is a decent approximation in this case. We make the approximation that the mole fraction for the water is actually 1. Again, the mole fraction of the water would actually truly be less than 1, and maybe in this case actually significantly less than 1. But it's the approximation we're making for simplicity, really. In that case, our reaction quotient is the molar concentration of ADP, the molar concentration of pyrophosphate, the molar concentration of ATP, and there would be a mole fraction for water underneath here as well, but we're setting that equal to 1, and so it doesn't appear in our expressions. Now all we have to do is plug in values, 10 to the minus 3, 1 millimolar for this guy, 20 millimolar for this guy, 3 millimolar for that guy, and that gives us 6.7 times 10 to the minus 3 unitless quantity for the reaction quotient. Now, if we look at this expression for the reaction quotient, it doesn't look like it should be unitless, right? This should have units of molar, that should have units of molar, that should have units of molar, which means the overall, it looks like the overall reaction quotient should have units of molar as well, but that's because we're being a little sloppy here, right? These are really activities, and activities are always unitless. So all 4 of these guys up here are really unitless quantities. That means the reaction quotient is also always a unitless quantity. It looks like the reaction quotient has units here because we're ignoring these denominators, right? The activities are all unitless in their own right, and if we put the denominators in here, we would see that Q is actually a unitless quantity, in fact. So this quantity here over here doesn't have units. All right, now all we have to do is plug our Q value, our delta G0 value here, an RT into our formula, and when we do that, we get minus 43.5 kilojoules per mole, which is considerably greater, significantly greater than the minus 31 kilojoules per mole that you would get at standard conditions. So under typical cellular conditions, the driving force for the hydrolysis of ATP is actually a good deal stronger than it is at standard state conditions. And that means that the cell can actually make better use of the ATP that it has available to drive chemical processes, to drive molecular machines. It has more energy available to it as a result of ATP hydrolysis than it would at standard conditions. All right. Yes, this is just making the condition, or making the point that I've been making all along here, which is that the way you set up Q has to match with the standard state conditions that are assumed when you choose a value for the delta G0. Under sort of freshman conditions, all these worries about standard state matching and so on don't usually show up because the problems have been carefully chosen so they don't show up, so that these complications don't confuse students. But under more general conditions out there in the wild, in the real world, these kinds of complications do show up, and they show up fairly frequently. So in this class, which is, of course, more rigorous and more advanced than freshman chemistry, I will emphasize these standard state issues in order to make it possible for people to deal with the complications that show up in real life. All right, so let's talk about the standard states. We haven't really talked about that before. I've just been sort of assuming what standard states are without talking about them in detail. There are a bunch of different standard states. Out in the wild, you'll encounter all kinds of different ones. But there are two that are the most common. One is called the chemist's standard state. The standard state conditions are that all solutes are at 1 molar concentration, all gases are at 1 atmosphere concentration, or sometimes 1 bar concentration. Remember that 1 bar is equal to 1.013 atmospheres, and so it's just a little bit bigger than an atmosphere. It's only about 1% difference from 1 atmosphere. So whether it's 1 atmosphere or 1 bar usually doesn't make very much difference. And some tables use bars, some tables use atmospheres. Bars are nicer. Bar is an MKS unit, so it's a little bit nicer in some ways than atmosphere. On the other hand, atmosphere is so widely used that it's oftentimes the more convenient choice too. And then finally, for all solvents, like the water in the example above, or solids, then we assume that the standard state conditions is that all of those things are pure. That is, the mole fractions for them are all 1. There is, however, a second, so that's the most common standard state. Most of the thermodynamic tables that you look at assume this standard state. If you look in a good thermodynamics tables, there'll be a header above the table that tells you about what all the standard states are and a bunch of other technical information. And most of the time, and you should check that out, be careful what the standard states are before you start using numbers from a table willy-nilly. Make sure you know what standard states are being assumed. And most of the time, for most tables, it's this standard state that's being assumed. However, when it's biochemical processes that are sort of the context for a calculation, very often this other standard state called the biochemist standard state gets used. It's the same as the chemist standard state. Solutes are all assumed to be at 1 molar concentration. Gases are at 1 atmosphere or 1 bar. Solvents and solids are pure, except for hydrogen ions, and those are assumed to be at pH 7. The reason for that is obvious, right? And that is that pH 7 is around the concentration. That's 10 to the minus 7 molar, right, for H+. 1 molar H+ would be crazy for most biochemical situations. It's much smaller concentrations of H+ for most biochemical situations, even if the pH isn't 7, as it usually isn't inside cells. It's usually around 8 or so inside cells. So that's 10 to the minus 8 molar H+, even though, you know, pH 7 isn't really the condition inside cells. It's in the ballpark, at least. It's way different, way closer to being cellular conditions than 1 molar H+ would be. 1 molar H+ corresponds to pH of 0. It's a pretty strong acidic solution. That sort of condition never exists inside biological systems. And so for biologically related stuff, we assume that H+ concentration, the pH, basically is in the neighborhood of 7. That's the standard state. All right. The standard state for the delta G0 value for the hydrolysis of ATP that I used up here in the previous example, that's actually using the biochemist's standard state. And there's no H+ in this reaction, so it doesn't actually matter. So it turns out that the biochemist standard state and the chemist standard state are the same for this particular reaction. But any chemical reaction that involves H+, like an acid-base reaction, for example, it matters very much. You'll get very different numbers in the biochemist standard state than you will in the chemist's standard state. So you have to be careful to watch for that. In general, thermodynamic tables will tell you what standard state they're using, but if you're not paying attention, you might not be aware. And in that case, your numbers that you get from that table might mean something very different than what you're assuming they mean. All right, so that's a bit about standard states. Now let's look at another example. And in this example, I chose this example to illustrate the fact that if you have a reaction quotient with a bunch of activities, so in general something like this, right, for the generic chemical reaction, it's this, that it doesn't have to be the case. We've already seen one example a little bit, but it doesn't have to be the case that all these activities are the same kinds of things. They don't have to all be concentrations. They don't have to be mole fractions. They can involve pressures and other kinds of measures of concentration if that's convenient and if that's in keeping with the standard states that you use to get a delta G value. So in this particular reaction, we have one reactant that's in the gas phase, right? So pressure is going to be, the pressure of the O2 is going to be the sort of natural concentration unit, quote unquote concentration unit that you're going to want to use. You could use molar concentration for a gas. People do that. It does happen, and you got to be a little careful to make sure that, you know, what's been assumed for the standard state. But for most standard state situations, because O2 is a gas, pressure is going to be the thing that you're going to want to use for the activities for O2, not molar concentrations. It also involves some acetic acid, which is dissolved in a water solution, so it's aqueous. In that case, we're going to want to use the 1 molar concentration. So pressure equals 1 atmosphere. It's going to be the relevant standard state for the oxygen. 1 molar is going to be the relevant standard state for the acetic acid. Over here on the product side, the carbon dioxide is also a gas, so 1 atmosphere is going to be the relevant standard state. And finally, we have the water, which we're going to assume is the solvent. So pure solvent, or mole fraction equals 1, is going to be the standards, the sort of natural standard state for that particular product molecule. And so, when we go to choose our activities for oxygen, I choose the partial pressure of the oxygen divided by the standard state pressure of 1 atmosphere. For the acetic acid, I choose the molar, it's a solute, right? A dilute solute. So I choose the 1 molar, I choose the molar concentration units and a 1 molar standard state. For the CO2, I choose pressure, partial pressure of CO2 in atmospheres for my activity divided by the standard state pressure of 1 atmosphere. And for the water, since it's the solvent, I choose the mole fraction definition of the activity, and then I'm going to assume that it's 1, again making the approximation that these other species are not present in high enough concentration to worry about. I mean, this mole fraction is probably more like 0.97 or something like that. It's a little bit off from actually 1, but usually those small concentration or activity differences aren't big enough to worry about. After all, I mean, just as a general comment, these calculations that we're doing involve other approximations that I'm really not bringing up, and so anything that's 97% accurate is probably, I mean, doing better than that is probably going to be undone by the other approximations that we're not worrying about. These calculations aren't accurate to better than 97% anyway, and so making this approximation is consistent with other approximations. All right, that means that our reaction quotient then would be, let's see, in general, in terms of activity, it would be the activity of the CO2 squared, right? Activity, looking at our reaction up here, there's a 2 there. Activity for the H2O quantity squared. Activity for the oxygen to the first power, and activity for the acetic acid also to the first power. And now substituting in these choices for activities, we get pressure squared for CO2, mole fraction for water squared, but we're assuming that mole fraction is 1, pressure for the oxygen, and molar concentration for the acetic acid. And so our reaction quotient therefore involves both pressure units for the gases and molar concentration units for the solutes. And that looks funny. It looks different than what you're used to from freshman chemistry and maybe from other classes, but it's perfectly valid and fine. In fact, if you are not careful, if you used molar concentrations for all of these things, for example, and then you got thermodynamic numbers from a table that had the usual standard states, you'd get the wrong answer, and way off on the wrong answer, in fact. All right, I'm not going to go further with this. We could plug numbers in here now and do calculations, but we did that earlier with ATP, so I don't see any great value in doing that again here. There is a homework problem that is meant to emphasize and give you some exercise, some practice in dealing with standard state issues and choices for activities issues. That's homework 5, third graded problem, graded problem, where the reaction in question is the dissolving of gaseous CO2 into water. So it's a transfer process, a molar dissolving process. And for that process, for that kind of situation, the usual way to do the calculation is to use Henry's law. You've seen this maybe over and over, but at least for sure in freshman chemistry. And Henry's law says that the concentration, the molar concentration of CO2 dissolved in solution is equal to something called the Henry's law constant times the pressure of the CO2 gas, sometimes in units of atmosphere, but in a lot of tables it's in units of kilopascals. So it's a little bit of a weird pressure unit. And you've got to convert, if you've got pressure of CO2 in atmospheres, you've got to convert it to kilopascals in order to get the right answer out of Henry's law here. Also, you can tell by what's on the two sides of the equation here that this Henry's law constant must have units. We've got to get out molar units on this side. We're putting kilopascal units in on this side. And so the Henry's law constant must have units of molar per kilopascal. And so some strange units. Let me say something just generally. I've chosen one particular type of Henry's law constant, but if you go out there in the literature, if you Google Henry's law, for example, on the internet, you'll see a whole bunch of different definitions for Henry's law. There's a whole bunch of different types of Henry's law constant. They all have different units. And so this is one example of that, but there are others. All right. Where does Henry's law come from? What does it have to do? I mean, this is a dissolving process. It's something that we should be able to deal with and treat by all of the thermodynamics that we've been talking about. It looks like exactly the kind of problem that we should be able to treat with delta G equals delta G0 plus RT log Q. So what is the relationship between this and Henry's law? Well, it looks like this Henry's law should be an equilibrium constant, right? We should have, if we use this approach, our approach that we've been using all along, we would get that the equilibrium constant is equal to the reaction quotient at equilibrium. For this particular reaction, that would be the activity of the CO2 in the aqueous phase divided by the activity of the CO2 in the gas phase. And if we rearrange that, we would get something that looks very much like Henry's law here, except that we have activities here, and we have an equilibrium constant rather than these concentration and pressure units and the Kh value. Remember that the activity for CO2 in the aqueous phase should be chosen to be the molar concentration of CO2 divided by the standard state molar concentration. The pressure should be the pressure of CO2 divided by the standard state pressure. But in this case, in order to match things up with Henry's law here, we want to choose our standard state pressure to be 1 kilopascal, not 1 atmosphere. And so I divide here by 1 kilopascal. That means this pressure has to be in units of kilopascals. So we're using a different pressure unit because of our different standard state. Then if I rearrange this, I get that the molar concentration of CO2 is equal to the equilibrium constant times a number that's just a 1, right? It doesn't make any change at all in the value of the equilibrium constant, but it has units of molar per kilopascals, which is exactly the units of the Henry's law constant, which means that this whole quantity here, the equilibrium constant, times this number which has a value of 1 but has units of molar per kilopascal, that is the Henry's law constant. And then times the pressure, which has now units of kilopascals. So Henry's law is just an example of what the kind of thing we've been doing all along here, except that it's been massaged and manipulated around to be a little bit more convenient for people who are just coming in from outside and not doing a full thermodynamic analysis. The Henry's law constant is an equilibrium constant, except for this extra units factor. And also except for the fact that the standard state conditions are a little bit unusual, kilopascals instead of atmospheres. All right, so I don't want to do the actual problem here because that's for the homework, but that's a little bit of background for that homework problem. And also you can see now for what reason that homework problem was put in the first place. All right, the next topic I want to talk about, I think I will stop here and save that for the next lecture.